Lecture 20. Black holes, wormholes, and time travel.
We just finished covering Einstein's theory of relativity, which lends itself to a substantival view of space-time. We saw that space-time is not necessarily substantival. In fact, Einstein didn't want it to be and didn't think it was. But that certainly is a consistent interpretation of relativity. And if we assume this view for the sake of argument, we're left with a four-dimensional view of the universe. The universe is one big chunk of four-dimensional space-time in which events and objects are situated. There are reference frames in the universe in which their subjective relations, like simultaneity, are different, but the relations within that four-dimensional block of space-time are objective and fixed. But this gives rise to some interesting questions that exist on the borderline of physics and metaphysics. If the universe is a giant block of space-time, or even if it's just a giant collection of coexisting space-time related objects and events, what modes of travel are possible within it? Does this mean that we can travel in time? The same sorts of questions arise when we think about temporal ontologies that are incompatible with free will. If the future exists before it occurs, can we travel to it? And if past events still exist even after they occur, can we travel to them? Now the question, can we travel in time, is too simplistic. It's like asking if we can travel in space. Of course we can travel in space. The interesting question is what kind of limits exist regarding how we can travel in space. For example, we've seen that we cannot travel in space faster than the speed of light. So, can we travel in time? Of course we can. We're all traveling forward in time at a constant rate. The better questions are these. Can the rate at which we travel in time be altered? And if so, can we have voluntary control of that rate? Can we change the direction through which we travel in time? Could we travel to the past? Could we skip over moments in time to arrive directly at some distant future or distant past moment? These are the questions I want to consider today. First, can the rate at which we travel in time be altered? We saw last lecture that, yes, indeed it can. Objects move through time more slowly the closer they are to a source of gravity. So, if you want to travel through time more quickly, become an astronaut and travel to the International Space Station. At that distance from the Earth, astronauts do experience time dilation and therefore experience more time. Time passes more quickly for them than it does for us here on Earth. Unfortunately, the amount of time dilation you would experience by becoming an astronaut is inconsequential. Even if you spent your entire life on the space station, upon returning, you would not find a significant difference between your age and the age of those you left behind. Besides, it just means that you would age more quickly. And who wants to become an astronaut and travel in time only to return and find that your friends are younger than you? If only we could somehow do the opposite and figure out a way to slow the rate at which you experience time. Experiencing only 10 years of change while the rest of the world experience 100 would be like traveling to the future. This is theoretically possible. The closer you are to a massive object, the slower time passes. And the more massive the object, the slower time passes. So if you could get as close as you can to a really massive object, time would pass very slowly for you, while it would pass comparatively quickly for others. Where might we find such massive objects? At the center of galaxies. They're called black holes. Black holes are objects so massive and thus bend space-time to such a large degree that if anything gets too close to them, including light, it cannot escape. That is why they are called black holes. We can't see them. They neither emit nor reflect light because they pull all light in. The basic idea behind black holes is over 200 years old. The English natural philosopher John Michell proposed their existence to the Royal Society of London in 1783. Later, their possibility was entailed by Einstein's relativity, and in 1939, Hartland Snyder and Robert Oppenheimer gave the first modern description of their properties. At first, they were only theoretical entities because they cannot be directly observed. Because light cannot escape them, they can't be seen. But today, most astrophysicists believe they are real and have been detected. Roughly put, even though they can't be seen, their interactions with surrounding matter can produce X-rays, and X-rays consistent with the existence of black holes have been detected in numerous places. The strongest candidate for a black hole is an X-ray source named Cygnus X1. There are other hypotheses about what produced these X-rays, but they're quite extreme. Real existing black holes are the most likely explanation. Now, you can't get too close to a black hole, otherwise you get sucked in and can never escape. But if you could take a spaceship in orbit around the event horizon of a black hole, the area beyond which nothing can escape, you would experience extreme time dilation. To those in the outside universe, it would seem as if you were almost frozen, but you would experience time passing normally. Once you emerged from the event horizon, you would find that much more time had passed in the universe than you had experienced while orbiting the black hole. The longer you orbited, the greater time difference there would be between your experience and that of the rest of the universe, and so you could even have control of how far in the future you traveled. But unfortunately, this is not a feasible method of time travel. Not only do we not have spaceships that could make the journey, or that could escape the gravitational forces produced near the event horizon of a black hole, but the nearest suitable black hole is at the center of our galaxy, a good 36,000 light years away. There are likely smaller black holes nearby, but they would subject you to tidal forces while you're orbiting them that would rip you apart. But another possible way to experience time dilation is with what Newton called a mass shell. Basically, a mass shell is a massive sphere with a hollow center. Now, how could this help you experience time dilation? Well, recall, the closer you are to a massive object, the slower you travel through time. This effect is more significant the closer you get to the object's center of gravity. If you were to dig down 20 miles into the Earth, you would actually experience time more slowly than people on the surface. So imagine that the Earth is just like it is, except there's a roughly human-sized hole right in the middle. If you could get down into that hole, you would experience the most time dilation that the Earth can produce. Basically, that's as close to its center of gravity as you can get. And what's nice is that even though you would be affected by the Earth's gravity more than anyone on Earth while you were in its hollow center, since it would pull on you in all directions equally, you would be weightless. You would just float there, experiencing extreme time dilation. Once you crawled out of the hole, you would find that more time on the surface had passed than you had experienced while at the center. The problem with this method, beyond the extreme difficulty of hollowing out the center of the Earth and traveling to the center of the Earth, is that the Earth is just not massive enough to give you a pronounced effect. Yes, when you emerge, more time would have passed on the surface, but not that much more. To put it in perspective, even if we hollowed out the center of Jupiter, the most massive planet in our solar system, 317 times more massive than the Earth, time would still only slow down a 100,000th of a percent, at least according to my colleague Tom Concanon's calculations. Needless to say, you'd have to pine away at the center of Jupiter for quite a while to get appreciable results. Unfortunately, a mass shell massive enough to get significant time dilation would likely just collapse in on itself, perhaps forming a black hole, and trust me, you don't want to be in the middle of that. Another method for traveling into the future can be derived from special relativity, and you're probably familiar with it from science fiction. Someone traveling in a spaceship away from the Earth at near the speed of light, who then turned around and came back at near the speed of light, would return to find that more time had passed on Earth than he had experienced in his travels. You might have heard this referred to as the relative velocity time dilation, or the twin paradox, because if a single twin did this, you'd end up with twins of different ages. It happens because the person traveling is in 3 different reference frames. One inertial as he travels away, one non-inertial as he turns around, and another inertial as he travels back, while the person on Earth stays in one reference frame the entire time. This kind of time travel is a plot device in the Planet of the Apes movie. The astronauts travel away from the Earth and return, only to find that the Earth has aged thousands of years, while they only aged a few, and the Earth has, in the meantime, been taken over by damn dirty apes. But this method of time travel is not presently feasible. We have no such ship. It would have to go really, really fast for the effect to even be moderate, and you'd end up wasting most of your life traveling in the process. You'd have to travel at 0.99 the speed of light for 62 years, 31 going and 31 coming back, to return to find that 440 years had passed on Earth. Again, thanks for the calculations, Tom. Besides, that's not really time travel as it is conventionally conceived. I don't want to sit around aging more slowly than other people. I want to skip over moments in time, directly traveling from the present to the future. And if I did travel to the future, no matter how I did it, I'd want to get back, to return to the present. The methods we have talked about so far don't allow for such things. Fortunately, relativity does suggest that such time travel is theoretically possible. Let's look at the science to see how. The first method does involve a little waiting around, but it also allows for one to travel to the past. To understand it, we must first understand a discovery by Austrian physicists Joseph Lenz and Hans Thirring. They found that not only does a massive object warp space-time, but if it's spinning, it will cause space-time to spin in the direction of the object's rotation. Kind of like a cylinder spinning in a pool of water creates a whirlpool. It seems to me that this is more evidence for the substantival view of space-time. Thanks to the work of Dutch-born physicist Willem Jacob van Stockum in the 1930s and the American physicist Frank Tipler in the 1970s, we discovered that we could take advantage of this effect to travel in time, to the future and to the past. If your spaceship were pulled in by the rotation of a massive rotating cylinder, orbited the cylinder for a time, and then exited at a certain angle, you would find yourself in the past, a point in time before you were drawn in by the cylinder. The longer you orbit and the more severe the angle by which you exit, the further in the past you can go. And orbiting in a different direction will send you into the future. Fascinating, right? This really is entailed by general relativity. The only problem is that the kind of rotating cylinder that is required for this effect, yeah, it has to be infinite in length. And not only do no such cylinders exist, but it doesn't seem that they even could exist. Although there are real objects that have infinite properties, for example, black holes have infinite density, rotating cylinders of infinite length do not seem to be among them. But there is still hope, a possible method of time travel that, although currently technologically impossible, may one day be possible. It would utilize what's called a wormhole, which is best understood with a metaphor. Think again about a two-dimensional piece of paper with two dots on it. The shortest distance between those 2 points is represented by a straight line drawn on the piece of paper, but only if the paper remains flat. If you were to bend the paper into the third dimension so that the dots touched, you could travel between them directly, bypassing the line connecting the 2 points on the paper. The idea behind a wormhole is that space-time could be bent in exactly the same way. We could bend it through a higher dimension, often called hyperspace, so that different points of space-time touch. This would allow us to skip over the space-time in between and facilitate instantaneous travel between them. We could not only use this to travel great distances in space, but also to different moments in time. Now the good news is that we don't have to create wormholes because they actually happen all the time. In fact, there is likely one occurring near you right now. The bad news is they are super tiny, smaller than subatomic particles, and they blink in and out of existence so quickly that not even light can travel through them. But if we could somehow find a way to enlarge an already existing wormhole and keep it open, we could use it as a time machine. Could we actually do this? Well, not yet. A physicist named Kip Thorne realized that keeping a wormhole open would require circumventing something called the average weak energy condition. However, he also believes that something called negative energy could do it, so maybe one day. But even if we do, merely opening a wormhole large enough to travel through doesn't create a time machine. Travel through one end, call it end A, and you would just end up at a different place at the same time when you emerged on the other end, call it end B. But you can turn it into a time machine. Just make one end, say end B, experience time dilation, like in the twin paradox. Put whatever mechanism you're using to hold the wormhole open on a really fast-moving spaceship, and make the wormhole travel away from end A at near light speed, and then return at near light speed. As a result, end B will have traveled into the future. For example, while end A has aged only 10 years and 1 month, end B will have aged very little. Let's say it might only be 1 month old. But the two ends of the wormhole are still linked just as they were. As a whole, the wormhole can only have one age. And so in its reference frame, both of its ends are still the same age. So if you stepped into end A of the wormhole when it's 10 years old, thus entering the reference frame of the wormhole, you would emerge from end B of the wormhole at the moment in time that end B is 10 years old. But since end B has experienced time dilation, the moment of time at which end B is actually 10 years old is far in the future, roughly 10 years into the future. So you could step into end A and emerge from end B 10 years in the future. But the end A that would now be next to you would be 20 years old. It was 10 years old before you stepped in it and traveled 10 years into the future. So you could step back into end A and emerge from end B another 10 years in the future. And you could just keep repeating the process to travel as far into the future as you wanted. And if you wanted to travel back into the past, you would just reverse the process, stepping into end B and emerging from end A in the past. Now there is one limit. You couldn't travel further back in the past than the moment in which the wormhole was first created. So, unless some advanced civilization has already created a wormhole far in our distant past, this method of time travel will never get us there. But still, this is pretty damn cool. Will we ever do this? Well, the goal of those who study such things is simply to demonstrate what is consistent with relativity. Of course, physical or technological limits may prevent us from ever accomplishing this. But there also may be philosophical limits, logical limits that prevent such time travel, specifically time travel into the past. And this is where we get back into some really heavy metaphysics. Logical arguments against the possibility of time travel rely on the most fundamental axiom of logic, the law of non-contradiction. Contradictions are statements that suggest that a proposition is both true and false at the same time. The law does not merely state that contradictions happen not to be true. Rather, it states that it is not even possible for any contradiction to be true. In the vernacular of possible worlds talk, there is no possible world in which a contradiction is true. The truth of this law stands behind all logic, reasoning, and argument. Everything that we have learned as a species assumes the truth of the law of non-contradiction. The possibility of time travel seems to entail the possibility of a true contradiction. The argument that points this out is called the grandfather paradox. If I can travel into the past, I can travel to a point in time before my grandfather met my grandmother, and subsequently, I could kill my grandfather. Consequently, my father will never be born, and so I will never be born. But if I am never born, I cannot travel back in time to kill my grandfather, so I am born. So I can travel back in time to kill my grandfather. So I'm not born. You get the idea. Time travel seems to make it possible that I both exist and don't exist, that I both kill my grandfather and I don't. And that's a problem. And it's important to realize that you can't solve this paradox and make time travel possible by simply deciding not to kill your grandfather. This is how science fiction sometimes avoids dealing with this paradox. For example, we talked before about the TV show Doctor Who, about the time traveler called the Doctor. In one episode, when the Doctor and Martha, one of his companions, visits London in the past, Martha actually asks, "Well, what if I kill my grandfather?" The Doctor simply asks if she's planning to, and she replies no. "Well then," the Doctor says, as if the paradox is solved. But the law of non-contradiction doesn't merely state that contradictions aren't true. It says that they're not even possibly true. Since it seems time travel makes it possible for Martha to kill her grandfather, even though she doesn't, time travel makes it possible for a contradiction to be true, and that violates the law. But some philosophers, such as David Lewis, have argued this paradox can be solved, and not by denying the law of non-contradiction. That would make the entire edifice of all knowledge crumble. David Lewis argues that if you travel into the past, certain actions would be impossible to perform. If Martha were to attempt to kill her grandfather, she would necessarily fail. Why would Martha be restricted in this sense? It wouldn't just be a logical fact that she couldn't behave that way, it would be a physical fact. The action she performs while in the past would have already been written on the timeline of the past before she ever stepped into the time machine. In a sense, her future is already written, it's just that a portion of her future exists in the past. If a record was kept of her visit, Martha could have even discovered that she was destined to travel in time to the past before she even knew time travel was possible. And since those events are already written on the timeline, once she arrives in the past, she cannot perform any other actions than the ones it was already true that she would perform. And since, given that she was born, clearly none of those actions caused her to have never been born, it is impossible for her to perform actions that would entail that she never had been born. Such actions are not written on the timeline. Now, this seems to entail that Martha does not have free will when she travels into the past. She cannot do anything other than what it was already true she would do. But we're talking about time travel that is made possible by relativity, and we've already seen that relativity is incompatible with free will. So this shouldn't come as a surprise, and it certainly isn't a consequence that physicists defending time travel would be unwilling to accept. They already think Martha doesn't have free will before she hops into the time machine. Why would traveling in time make any difference? In a sense, according to relativity, Martha is no different than the rest of us. Our entire lifeline, including everywhere we will go and the actions we will perform, including what we now perceive as our future actions, is already written on the timeline. Remember, relativity suggests the block worldview, that all space-time events, including the events of our timeline, coexist in one giant block with their relationships in the block fixed. And we can't do anything different than what is written in the block, than what is written on the timeline. The only difference between us and Martha is that, as a time traveler, her timeline is cut up into pieces and scattered out of order throughout the block. So maybe time travel to the past is logically possible, but this means once you get there, you would not be able to change it. If you will travel to the past, the actions you will take when there have already occurred. They are already a part of the block. You can observe the past and participate in the past, but you cannot change the past. In fact, if you go back in time with the intention of preventing an historical event, not only will you be unable to, because the action of you failing to do so is already written on the block, but you might discover that you are in fact the cause of that event. This is a common motif in the Doctor Who time travel stories. The Doctor travels back to observe some past event, his companion wants to stop it, and they end up causing it. Doctor Who's been on the air for so long, he's responsible for just about every major event in human history, including the burning of Rome, the Great Fire of London, and the eruption of Mount Vesuvius. He apparently has a thing for fire. But there's another version of the grandfather paradox developed by the physicist Joseph Polchinski that is not as easy to avoid. He argued that time travel, specifically time travel through wormholes, can give rise to paradoxes even when we are not dealing with the actions of agents. Suppose you create two wormholes that were time dilated by a small amount, let's say 2 seconds, and you place them in front of two adjacent corner pockets on a pool table. Let's say that the time dilated wormhole is on your right, such that if you shoot the cue ball into that wormhole, it will emerge from the left wormhole 2 seconds earlier. Imagine you shoot the cue ball towards the right wormhole from the corner of the table diagonally across from it, and you give it a momentum that takes the ball 1 second to reach the middle of the table and 2 seconds to cross it completely and enter the wormhole. The ball then emerges from the left wormhole 2 seconds earlier. But 2 seconds earlier is the moment at which you originally hit the ball. So it emerges from the left wormhole at the same moment that you hit it towards the right wormhole. But the ball that emerges from the left wormhole at that moment will be traveling at the same velocity and with a trajectory that will cross the table in the opposite direction. So in 1 second, it will be at the midpoint of the table, at the exact same moment that it was at the midpoint after you originally hit it. Thus, it will knock itself off course and prevent itself from ever entering the right wormhole in the first place. This, of course, would prevent it from emerging from the left wormhole, thus preventing it from knocking itself off course, thus preventing it from preventing its entry into the right wormhole. You see the problem. Again, you can't avoid the paradox by deciding to never set up such a situation. Contradictions can't even be possible. The fact that time travel makes it possible to set up such a situation seems to entail that time travel is impossible. Can this paradox be solved? Well, not in the confines of this lecture. Some physicists have claimed to solve it by more accurately describing the possible trajectories the ball might have. I personally am not convinced. The fact that consistent trajectories can be described does not mean that inconsistent trajectories are impossible and they would have to be to avoid the paradox. But before we're done, there's one more paradox to consider. To understand it, we first need to realize that time travel would make causal loops possible. Situations where A causes B and then B causes C, but then C causes A. For example, if a past event causes you to be fascinated with it, but your fascination with the event causes you to travel in time to observe it, and then you end up causing it, then your fascination causes the event, and your event causes your fascination. A causal loop. In a 1969 time travel story by Michael Moorcock entitled Behold the Man, a time traveler obsessed with the crucifixion of Christ travels back to observe it, is thought to be the Messiah, and is in turn crucified. Such causal loops could lead to what's called a gin, a complex object or idea that has no origin. Suppose you find a time travel machine buried in a mine shaft. You figure out how it works, and then you use it to travel to the past, or you find someone, teach them to make the time machine, and then tell them to bury it in the mine shaft. Question: who invented the time machine? Where did the idea originally come from? A similar problem shows that time travel makes it possible for you to create yourself. In a 1959 short story called All You Zombies by science fiction writer Robert Heinlein, the main character, after some time travel and a sex change, becomes his own mother, father, daughter, and son. If such paradoxes can be resolved, time travel may help us make sense of what it means for something to be a self-caused entity. There actually is one version of paradox-free time travel, although some might contend that it's not really time travel at all. As we shall see in the next few lectures, there are reasons for believing that there is more than one universe, that the reality that exists is actually a multiverse. One conception of time travel suggests that if you were to travel to the past, you would not travel to the past of your own universe, but to the past of a universe identical to yours up to the point that you appear in the past. In fact, the act of time travel may be responsible for the creation of that universe. If so, it is not possible to travel into your own past and kill your own grandfather. But it is possible to create a new universe with a past identical to your own up to a certain point, and then make that universe's history turn out differently than yours. For example, in that universe, you could kill that universe's version of your grandfather, and thus prevent a version of yourself from ever being born in that universe. But since you were born in a different universe, that would not paradoxically prevent your own existence. There would not be jinns in a multiverse in which such time travel was possible. If you found a time machine in a mine shaft and traveled back to explain to someone else how to build a time machine, you would not be caught in a causal loop. You would just simply be creating a universe in which some other person learned from you, a person from a different universe, how to make a time machine. But after all this talk of multiple universes, do we really have any reason for thinking there are such things? That is a heavy metaphysical question about reality. Turns out we do. But to understand those reasons, we first need to understand quantum mechanics and the metaphysical issues it raises. So it is to those issues that we shall turn next.